Alright, I'm going to call this one two masses and a pulley. And what we're looking at here is a 15 kg mass, a 20 kg mass going over a pulley up here with a radius of 0.25. Now the questions are to ask the tensions in the string. So we'll call this tension T1, we'll call this T tension T2. Now the key to this question is to realize that these tensions are not going to be the same. And that's because what they're actually doing is this tension is going to be, tension 2 is going to be pulling on this pulley, and part of its force is going to go into rotating this pulley. So that's going to have to be subtracted off T1 to get T1's tension. You couldn't have a force being used to rotate a pulley and being used to go down here and pull it back. It's kind of like 2 for 1, right? So that's the key to this problem. Apart from that, it becomes pretty easy. We've got 15 kgs there. So we've got a force going back that way. That force is always mg sine theta. And we need a net force of 30 newtons. The mg sine theta gives you an 88.46 newton force that way. We need 30 newtons to get the 2 meters per second, which was the acceleration. So we know we have to have 118.46 newtons in T1. Now T2, again, a reasonably simple one. T1 has got 196 newtons downwards. We know that we actually only need 40 newtons downwards. So T2 must be equal to 156 newtons. Now that means we lost 37.54 newtons somewhere, and that 37.54, so T2 minus T1 equals 37.54 newtons. That must be what's accelerating the rotating disc. So looking at our formulas, torque equals rotational inertia times the angular acceleration. If we put this all down, we know that that torque is coming from that 37.54. So 37.54 times the radius, 0.25, must be equal to I times alpha, which is really acceleration over radius. So we can say 37.54 times 0.25 squared, all divided by the acceleration, which was 2, will give us I. If we do all that, I think it comes out to 1.17 kilograms meters squared. And I think we are done.